Summary of lecture 25, part 2. This will be the summary of the lecture. Okay, we have learned about the real matrices, the symmetric real matrices, and those are our good cases. So let's write down the good matrix. Again, here is the one with the real eigenvalue and also perpendicular eigenvector axis. Okay, and now in this part we will discuss about a specific case of that symmetric matrices, which are called the positive definite matrix, where the eigenvalues are positive. So it's no longer real because it can be negative or positive. We're mainly interested in the case where the eigenvalues are all positive. And it comes to question, okay, so how to check the sign of the eigenvalue? Well, we can compute all the eigenvalues, of course, but imagine if we have like 50 by 50 matrix or 100 by 100 size of matrix, then this is particularly not the fastest way or the most efficient way. And that's where this trick came, this using pivots to dictate or to tell us what is the sign of the eigenvalues. And why is that? And well, it's naturally what you have learning in the determinant case or even in the pivots in the earlier lecture. Well, you have some matrix here, A, B, C, T and everything. And then you can do the elimination, so you have the pivot here. Okay, let's give this a proper ratio. So the proper ratio will be something divided by A. It will be, okay, so C multiplied by the first row, okay, B, something like this. And then I want to connect this form into the way we compute eigenvalues. The formula that we use to eigenvalues is that we subtract the identity eigenvalue from this matrix, right? So we have A minus something here, we kept this component the same, and then we have whatever value here multiplied by lambda, and then from here we computed the determinant. But if in the case where this is triangular, then we know already that this is the eigenvalues. So that's where I see the connection between the pivots and the eigenvalues. So here my eigenvalues 1 is A and my eigenvalues 2 is the D minus C E B. And this has to be positive, right? And this tells me that, well, if in the case where A is minus, then I will have negative eigenvalues as well here. Okay, and that's what I want to bring here. So again, the sign of pivots tells us about the signs of eigenvalues. But just remember that pivots is not the same as eigenvalues, right? So they can be a different number, but their values, their sign are the same. So that's just what we sometimes are interested in the sign of the eigenvalues, because that tells us about how the system will behave. And then another point is that if you remember from the determinant lecture, that the product of eigenvalues is the determinant, right? And that goes the same thing as the product of pivots, because in pivots you have basically all those determinant. So this also will be equal, so product of pivots, will equal to the product of the eigenvalues. Okay, now that's about this point. I just want to emphasize that the product of pivots is the one that we learned from the determinant lecture, rule number 10, where if we have this thing in the diagonal, then we can just multiply this diagonal and get the determinant. It's the product of the diagonal component, in this diagonal, and the product of eigenvalues is something that we learned recently to compute the determinant of the matrix. Okay. Now this brings us to our last point here. So what is the positive definite? Okay, you got the eigenvalues, but there is actually more. So what matrix can you say, what matrix constitute, what kind of criteria, that must be fulfilled in order for a matrix to be positive definite matrix? So first we have mentioned it here that the eigenvalues has to be all positive. Okay, we got it first. And then of course then the implication of the eigenvalues being positive is that the pivots also has to be positive. Okay, but this is not enough. Okay, let's say this example here. Well, this is not enough because we also mentioned briefly about the determinant. So we're saying that if this positive, then the determinant has to be positive as well. Well, let's quickly have an example. First is this matrix, also from the lecture. I'm borrowing this from the lecture, and then you can see that in the end we have this equation, and then we have the root of them, which are 4 plus minus root to the 5, and this will be all positive. Okay, and also the determinant is eigenvalues 1 times eigenvalue 2, so this will be also positive. Okay, and we say, okay, the determinant of a matrix to be positive definite has to be positive as well. But how about the case of this? Let's say we compute the determinant, this is 3, and then we conclude that this is positive definite matrix. Okay, although you might say, hey, we can clearly see that this pivot is not positive, so it can't be. But let's just say, so this conclusion that we have here by saying the determinant of positive definite matrix has to be positive kind of breaks down here, right? Because right now we can see clearly this is not positive definite, but the determinant also positive. So there's another thing that has to be checked in terms of determinant, which are the subdeterminant, which is here. So all the subdeterminant has to be also positive. Okay, so if you are here, you can see the determinant of this 1 by 1 matrix is positive, and the determinant of 2 by 2 matrix is of course also positive, 15 minus 4. And here the subdeterminant of 1 by 1 is minus 1, so it breaks already, it doesn't fulfill the condition, so we know that this is not positive definite matrix. And that's it. Thank you.